And another try. Hello and welcome back to CS422, Theory of Computation. We are talking about computational complexity theory. And to this end, we've introduced a refined model of computation, formalization of algorithm, namely with modified or wild programs and turn them into while plus program. So while plus program, in addition to the increment and decrement operation that we've already had in the previous model of computation, in the previous formalization of algorithm, now we introduce addition and subtraction, where subtraction, as you recall, the result is made sure to be non-negative, so subtracting a larger number from a smaller number will result in 0. Also, there's a new operation of division by 2, rounding down if the argument happens to be odd. And that's our new way of measuring computational cost. We now count the number of operations, including this now enhanced set of operations. And we measure the number of operations, the computational cost, in dependence on the binary length of the input, not in dependence on the value, but in dependence on the binary length of the input, which is defined in this way for single natural numbers. And when we have a tuple of natural numbers, then we count the maximum binary length. That's a subtle difference to what I introduced you in our last session. Last session, we defined the length of a tuple to be the sum of the binary length, but now we define it to be the maximum binary length. And the reason is that now the proof becomes simpler, that whenever a program, while plus program, makes t steps, then the binary length of its variables in this sense, as a tuple of natural numbers, will be at most t times larger than the binary length of the initial of the input. Let me say that again. In this sense, the binary length of all variables together, measured as this binary length of the tuple, the maximum length of all variables, will be at most t times the binary length of the not t times, but plus t, the binary length of the input. Or put differently, every single operation can increment the binary length, which is our abbreviation for the memory consumption, can increment that by at most once, and therefore making t steps, it will increase by at most t, so that in particular polynomial time while plus program will also have only at most polynomial number of bits, use a polynomial amount of memory. We've recalled our pairing function and observed that the pairing function and its inverse can be computed in time polynomial in the binary input length. And the new definition of the binary length of a tuple now is related to the binary length of the encoding combination of all the variables into one single natural number up to this constant vector k. Constant vector because k denotes the number of variables, and the number of variables of a while plus program does not change, does not depend on the input, and therefore is a constant. So base message to remember from here that each step can increase the amount of memory at most by 1 in this sense, and therefore when the while plus program runs in polynomial time, then it will only incur polynomial amount of memory. It will be a polynomial space program. Yes, and then we've analyzed arithmetic operations such as multiplication, which naively by repeated addition takes an exponential number of steps of additions, but using long multiplication, it boils down to a linear number of steps, a linear number of addition, and in particular polynomial number. And long division can also be performed, actually linear number of steps, using a variant of Newton's method, which I'm not going to discuss here. And the pairing function can be computed in polynomial number of steps and unpairing as well. And that led us to the introduction of this famous complexity classes in their study. And the complexity classes all evolve around polynomial growth. Polynomial growth meaning growing at most like a polynomial, some fixed arbitrary but fixed polynomial. And what really matters about the polynomial is the degree of the polynomial. And the reason this polynomial growth is considered and not, let's say, linear or quadratic or cubic is because polynomial growth is closed under composition. And this led to Edmond's thesis that polynomial running time is a way of formalizing efficient algorithm, as opposed to exponential time, which is firstly does not capture efficiency. Polynomial time algorithms are immediately blow up even for modest input sizes. Remember the table we discussed of different algorithms for different kinds of computers. And also exponential time is not closed under composition, because the composition of exponential with an exponential in general will be a doubly exponential, and continuing it will climb like a tower of exponential. Yes, and polynomial growth is closed under composition in two ways. First, the composition of a polynomial with a polynomial is again a polynomial, but maybe more importantly, the composition of a polynomial time computable integer function with another or the same polynomial time computable integer function is again a polynomial time computable integer function. And the latter is not immediately obvious. It follows, it can be seen from recalling that computing the first polynomial time integer function like f can result in an increase of length of the value. So when f receives an argument x of some binary length n, then f returns as output some value y, and the value of that the binary length of that value may be larger, possibly much larger than x. And then when feeding that y into the next computation of the function g, that means that the running time of g is, by hypothesis, again polynomial, but now polynomial in the binary length of y, not in the binary length of x, the first argument. But remember our discussion that a polynomial time algorithm can increase the binary length of its data at most polynomially, and therefore the binary length of y indeed is at most polynomially larger than the binary length of the original argument x. Or put differently, when now invoking the second computation of g with a possibly larger argument y, then the possibly larger argument y still has binary length polynomial in the length of the original argument, and therefore computing g on this argument y again runs in time polynomial not just in the binary length of the second argument y, but even polynomial in the binary length of the original argument x. So that we have this second kind of closure under composition. And then we got to the famous complexity classes, starting with the class B of polynomial time decidable problems. So here we're talking about and restricting ourselves to decision problems, not to function problems. And we consider those that are decidable in polynomial time polynomial in the binary length. So recall that what it means to be decidable, it means that there's a while plus program that on input of a natural number tells whether this number belongs to L or not. So it always terminates, and even more, it does so in a time which is polynomial in the binary length of the given natural number. But it only answers yes or no, because here we're talking about decision problem. So this is polynomial time decidable problems, as opposed to, let's say, exponential time decidable, or what we introduce next, the polynomial space decidable problems. These are problems that can be decided using an amount of memory, which is polynomial in the binary length of the input. So here it's polynomial amount of memory, and here it's polynomial amount of steps, polynomial number of steps. And since we saw and argued that any while plus program making a polynomial number of steps will use at most polynomial amount of memory, as we proved by induction, it follows that P is a subclass of PSPACE. So recall that each step increases the amount of memory used by at most once. So any algorithm that runs in polynomial time, like an algorithm deciding a problem in P, will automatically also use at most a polynomial amount of memory, and thus be an algorithm pertaining to the class PSPACE. So that led us to our first, not too hard, inclusion between complexity classes. Then we've moved on to the complexity class X of exponential time decidable problems. Remember that these are not necessarily closed under composition. And we observed that this class includes the already introduced class PSPACE of polynomial space decidable problems. And this is an important but subtle argument. So let us use the opportunity in time to recall this proof. And here this proof is based on the observation that if a machine, if a while plus program uses at most S memory, remember memory means the largest binary length of any of the variables, then it must have at most 2 to the O of S distinct configurations, where a configuration is a kind of like a snapshot of a while plus program in its execution. So a configuration is a recording of all the variables, K, constant number of variables of the program at the time of the snapshot, as well as the number of the program counter. That is kind of the line number within the while plus program that is currently being executed. So put differently, a snapshot is kind of the information about a while plus program needed and sufficient in order to kind of store that program's execution on a, let's say, a hard drive, and then being able to resume, to reload and resume that program's execution transparently without the program even realizing it had been swapped out to the hard disk. And the same argument now shows that indeed when such a program has at most S memory cells, then first thing is that the number of distinct configuration can be at most exponential in this. So where the big O now depends on K, the number of variables, and this number of configuration is exponential. Let's discuss that, because with S bits, that means the overall every single memory cell having at most S bits means can have at most 2 to the S different values, right? So every bit can have 2 possible values, 0 or 1. So S bits can have at most 2 to the S different values. And here we're not just talking about S bits of memory for one variable, but we're talking about S bits for up to K, a constant number of variables, and therefore the number of distinct configuration is at most 2 to the O of S, where here the big O depends on K. Furthermore, this number of configuration includes the count of the current program counter, which is also bounded at most by S. So long story short, that means that any algorithm that runs in polynomial space will can only go through exponentially 2 to the O of S many configurations. Otherwise, if any configuration repeats, then since we're talking about deterministic wildpath programs, it means it implies that some configuration occurs repeatedly. And when a configuration recurs repeatedly, it means that, let's say a second time, it means that both the program counter and the values of all the variables are the same as some time earlier. And therefore, since it's a deterministic program, it will repeat all the steps followed when the configuration had been established the first time until the configuration becomes established a second time. But since the configuration is the same as the first time, also the subsequent program execution will be the same as the second time, and therefore will eventually repeat it for a third time, then for a fourth time, and will keep repeating indefinitely, so that any wildpath program using at most S memory cells, when it happens to, for some reason, encounter more than 2 to the O of S memory configurations, that means that this program is already caught and trapped inside an endless loop and will continue computing on forever, indefinitely, and thus raise a contradiction, because the problems we consider here, running in polynomial time or polynomial amount of memory, any such computation is required to eventually terminate according to our definition. So in particular, it will never run indefinitely, and thus by contraposition, it means that any such program will must have at most an exponential number of configurations and will make at most an exponential number of steps. And this proves that PSPACE is included in exponential time. Any PSPACE program will make at most a single exponential number of steps. That gave rise to our next inclusion of this hierarchy that is gradually filling up. And the final complexity class that we introduced was the famous P versus NP, the NP complexity class. And let me take the opportunity to clarify some popular misconception about NP, because NP is sometimes misunderstood to mean not polynomial time. And that's, of course, a misunderstanding, because not polynomial time would mean this is a class which is actually even disjoint from the class P of polynomial time decidable problems. So instead, NP is the abbreviation for non-deterministic polynomial time. And right now you are not even supposed to understand what non-determinism means. We're going to return to that question at the very last slide of this lecture. For now, let's instead take an approach and syntactic approach, and define NP simply to be the class of all polynomial time verifiable problem. Yeah, polynomial time verifiable means problems of the following form: the set of all natural numbers x to which there exists a natural number y of length at most polynomial in the binary length of the argument x, such that whenever x belongs to this decision problem L, then the pair x comma y can be confirmed by the decision problem V, a so-called verifier, whereas in the other case, when x does not belong to the decision problem L, then there must not exist any such y that makes the verifier terminate and accept in polynomial time. So for now, this looks like a little bit a random definition, but let me remind you that we had a similar definition when we talk about semi-decidable problems. Namely, we had this normal form theorem, which would imply that any semi-decidable problem is of a similar form, except that semi-decidability without complexity drops the requirement that y must polynomial time at most polynomially long in the binary length of x. The general setting of semi-decidable or recursively enumerable means that y for a candidate witness can be arbitrary as long as it can be verified to be witness. Here we required it to be verifiable as a witness in polynomial time. So that's kind of a strengthening of a quantitative version of the condition for a problem to be semi-decidable, and here we want it to be kind of polynomially semi-decidable, and this is for historical reasons. This is called a problem which is syntactically in the class NP, because here it's required to have this particular syntactic form. And at the end, as I said, we're going to introduce an equivalent and establish an equivalent, but semantic version of NP. Okay, so that being said, let's return to our small hierarchy here, and let's see whether and where NP fits into this hierarchy. And fortunately, it does. It lies between P and PSPACE, and frankly, nobody knows whether it is strictly contained in, between P and PSPACE, or whether it coincides with one of the two classes and with which, or possibly both. This is indeed the Millennium Prize problem that awards you $1 million. So the claim says that this new class NP lies between the classes P and PSPACEs. So let's have a closer look at these two classes and how they relate to each other. The first observation that the class of polynomial time verifiable problem includes the class P of polynomial time decidable problems. To this end, observe that we don't really need any such witness y, so we can bring the polynomial time decidable problem into this form by considering kind of a dummy verifier, a verifier that when presented with a encoded pair x comma y simply ignores the second argument. First recovers our first argument by decoding the paired value, then recovering x, and then invoking the polynomial time decidable algorithm on x while ignoring y. And this kind of dummy verifier is indeed obviously polynomial time decidable, because the polynomial, the binary length of the pair x comma y is at least and at most polynomial in the binary length of x. It's at least because here we only include something more, namely y, and at most polynomial because my hypothesis y, the way it's considered, although it's later ignored, is a polynomial in the binary length of x. So long story short, this shows that polynomial time decidable problems is a subclass, possibly proper, but nobody knows, of the subclass of polynomial time verifiable problem. And finally, what remains to conclude and establish this small hierarchy finally is to show that NP is contained in PSPACE. So in order to show that, let's consider a prototypical NP problem, namely a problem of this polynomial time verifiable form here, which asks whether there exists such a witness y. And but in order to decide that problem in PSPACE without verifying, we need to arguably test all possible candidate witnesses Y. And superficially, it seems like there are too many, there are exponentially many of these witnesses Y, because how many binary strings are there with binary length is, let's say, at most 100. Right, 2 to the 100, right? And how many witness strings are there with binary length is at most polynomial in the binary length of X? Well, it's at most exponentially many. So in order to decide whether X belongs to L, where L is in the class NP, we have no better idea. For 50 years, nobody has been able to come up with a better idea than to test all possible candidate witnesses Y, of which there are exponentially many, and thus this algorithm for the complexity class NP would run in exponential time, but that's not our concern right now. Here we're concerned with the amount of memory, and the amount of memory here is indeed bounded polynomially, because any such program, any such computation can do that now try all possible candidate witnesses Y. Let me say that again. In order to prove that NP is contained in PSPACE, we fix a polynomial time verifier problem, that is a problem of this form, and then kind of simulated or executed without the witness by trying all possible candidate witnesses, and although they are exponentially many and thus incur exponential running time or slow down, in terms of memory consumption, these witnesses are not bad at all, because remember, running time is measured in dependence on the binary length of the original input, and so we can try all possible candidate witnesses Y and reuse the memory used both for storing the current candidate witness Y, as well as resuming the computation when proceeding to the next candidate witness. So long story short, that means we only need one fixed amount of memory, like 50 bits for X, in order to test all possible candidate witnesses Y. And when trying the next one, reuse the same area of memory. So trying all of them takes exponential time, but only a polynomial amount of memory, and thus establishes this inclusion. So that was all brief recap from last time with this hierarchy. And as I emphasized, it is not known whether and which of these inclusions are strict, this, or all of them. What is known, and what we will maybe show later in the advanced complexity theory, is that P is a proper subclass of exponential time. They are all problems that can be decided in exponential time, but probably not in polynomial time. So this is a hierarchy, and now we want to classify some real-world decision problems in this hierarchy and see into which class they belong. And we're going to particularly consider graph problems. And to this end, we need to discuss some ways of encoding graphs as integers. And remember that for a fixed number of variables, the binary length of the encoded value, all variables combined as one single natural number, is asymptotically as large up to constant factors as the binary length of the largest variable, which we use to denote this, and where the binary length of some variable of the natural number turns out to be basically the logarithm of the value. So huge difference between value and binary length. Binary length is the logarithm of the value. The value is exponential in the binary length. And we're going to use that. We're now encoding a graph, let's say a directed graph, a finite set of vertices. The number of vertices is usually denoted by small n. The number of edges is usually denoted by small m. But in our polynomial setting, this really, first of all, let me emphasize that there's a misuse of notation, because n both denotes the number of vertices of the graph and the binary length of the input, right? And this superficially, this could lead to some confusion and contradiction, because the same symbol is used to denote two different things, but the two different things are polynomial related, so that as long as we're only talking of polynomial amount of memory or polynomial running time, it makes no difference whether we measure that running time in terms of the number of vertices n of the graph or the binary length n of the input. And when the graph we're considering is undirected, that means that to every directed edge, graphs here have a directed edge to begin with. To every directed edge in one direction, there's also a directed edge in the opposite direction. This is how we encode undirected graphs. Sometimes we consider graphs, directed or undirected, which are equipped with weights to the edges, sometimes also weights to the nodes, but here focus is on edge weights. That is, they exist and we're provided with a function which is traditionally called C, from the edges to the natural numbers, to the non-negative integers, that assigns weight to every edge. Now, how to input such graphs into Wild Plus programs? Anything that can be input or that is output by a Wild Plus program is and must be a natural number, and it's up to us how to interpret the value of that natural number, how to assign a meaning to that. And when we talk about encoding graphs, that means we will consider the adjacency matrix of that graph, which is a matrix of natural numbers, zeros and ones, as long as it's an unweighted graph, possibly other natural numbers as well, if it's a graph with edge weights. And but again, the binary length of this adjacency matrix encoded as a tuple of k times k integers, right? K times k, the size of the matrix. The total binary length is asymptotically the same as the number n of vertices up to a polynomial. And this adjacency matrix has as entries the weights of the non-negative integer weights of the graph that we want to encode, as you see here. And if there's no edge, then we agree to the convention to say that the entry at the adjacency matrix is infinite. In most practical purposes, one can instead also choose some very large natural number, much larger, for example, than the largest weight that is assigned to an edge that is actually present. And when the underlying directed graph happens to be undirected, Remember, undirected means here that to every edge, there's also an edge in the opposite direction. This means that the adjacency matrix of that graph is encoded as a symmetric matrix. And in this case, we only need to store the symmetric part, and we will not bother with the redundancy of the other half of the adjacency matrix. But that's just a convention for convenience that we use here. And yeah, for all sequable and practical purposes, remember that we've already started silently, secretly switching back and forth between different interpretations of the number n of vertices. And here we're going to extend that to weighted graphs, and we observe that the binary length of a graph with edge weights, which is this quantity, right? This is the encoding of a graph with the edge weights in this sense here as adjacency matrix. This is at least the number of vertices of the graph, right? Of course, every vertex in the graph will need at least one bit to store in the adjacency matrix on the one end, but on the other hand, it's also at most polynomially in the number of vertices, which is, namely specifically, it's at most quadratic in the number of vertices times a factor that measures the binary length of the largest edge weight. So if there's some very large edge weight, then this quantity may be very large, which actually is good for us, right? Because if we measure, as long as we measure the running time independence on the binary length of the input, if the input has a very long binary length because it has so large weight, then it's easier to have an algorithm running time polynomial in that very long binary length. So the long story short, for all practical purposes, we can, and in the sequel, we will maybe silently move back and forth between both conceptions, measuring the computational dependence on the value of the number of vertices, or measuring computational cost independence on the binary length of the overall input, that is including and taking into account the binary length of the edge weights. And now we can start looking and investigating some first example problems. And the first example problem we're looking at is 3 coloring. So coloring of a graph is a mapping that assigns to every vertex some color, and it must be so that adjacent vertices that are constitute both ends of some edge must be assigned different colors. Let me say that again. A coloring assigns color to every single vertex. In this case, we're interested in 3 colors. So it assigns one of the 3 colors, red, green, blue, to every single vertex. And secondly, whenever 2 vertices are joined by an edge, then the colors assigned to these vertices must be different. Or put shortly, there must be no monochromatic edge. Say it again. Coloring means that there's no monochromatic edge. And of course, we can always color a graph without monochromatic edge, provided that we have a sufficient number of colors, right? So if we have like a different color available for every vertex, then we can simply color every vertex with a new color, and then there will be no monochromaticity at all in the entire graph, whether there is an edge or not. But when we restrict the number of colors to 3, then it may be infeasible to satisfy that constraint, may be impossible to assign one of the three colors, red, green, and blue, to the vertices without ending up with two adjacent vertices having the same color. Let's consider some examples, shall we? So here's an example which is called the Peterson graph. Peterson graph is this graph. It's very nice because it's so symmetric, right? And the message here is this graph admits three coloring. This graph admits a way of assigning the three colors, red, green, blue, to its vertices in such a way that every edge is not monochromatic. And what you see here is precisely such a three coloring. You see every vertex here of the Peterson graph is colored in one of these three colors, red, green, blue. And also you observe that no edge is monochromatic. The endpoints of any two vertices that are on the same edge have a different color, right? So here these have the same, but there's no edge between them. The condition is only about edges in the graph. And so these two vertices have the same colors, but there's no edge between them, and thus it is permitted to color them in the same way. Now let's do the following and modify the Peterson graph a little bit, adding another edge. Now what you see here is that now this edge violates the three coloring property, right? So what used to be permissible coloring, one where any edge receives different colors on its end vertices, now this condition is violated here, but still this graph can be colored with three colors, namely just in a different way. And to see this different way, we're going to just rotate the graph, exploiting its symmetries. And thus now we arrive at the graph where the original three coloring by three colors actually constitutes an admissible coloring, because now the edge, which was a violation here, this edge kind of intuitively has moved here, and now is the part of this here, this new graph does not have such a vertex anymore. So that also this modified Peterson graph, in spite of having broken its admissibility, it's now still three colorable. Now let's continue this example and consider an even more restricted version of the Peterson graph, namely by throwing in yet another edge. So here we're throwing in another edge, connecting again the two red vertices and thus violating the three coloring property, but instead we can again apply some transformation of the graph, namely a rotation, so that this graph now still admits a three coloring, and this monochromatic edge is not present anymore, namely by rotating the coloring of the existing graph. But when we now add a third edge, then this graph resulting Peterson graph, well, it's not fair to call it Peterson anymore, but anyway, the new graph, which now has three edges added, that graph violates three colorability. Now it's really impossible to color this graph with three colors while satisfying the non-monochromaticity condition. And yes, so see this edge here does not work because it makes these two monochromatic. This edge that we considered before is not under consideration anymore. So summary, the property of being three colorable is a non-trivial property. Some graphs can be 3-colored and other graphs cannot. And thus it constitutes an interesting decision problem whose computational complexity it's worthwhile investigating. And to do so, we're first going to formalize this decision problem, namely as a set of all codes, encodings of graphs that admit a 3-coloring. Remember, this is our way of formalizing decision problems as such of subsets of natural numbers. In this case, this is a set of all codes as natural numbers of such graphs that admit a 3-coloring. And the first observation is that this decision problem belongs to this complexity class NP. It can be formulated equivalently as a set of all graphs to which there exists some certain witness, which we here call Y. So this is because we've introduced the class NP as a syntactic class, a class which is defined in a certain form, and then we need to, in order to show 3-colorability as a part of that class, we need to reformulate 3-colorability in this form, and that's actually not too hard because what would we introduce as witness and what would we introduce as verifier? Well, verifier is already there, namely the decision the property of being a 3-coloring. Let me say that again. Consider the 3-coloring that is such a mapping, and put that mapping into a table, right? So value table of that mapping, assigning one of the 3 colors to every vertex. And when presented with that table, then it's easy to verify whether or not that table constitutes a valid 3-coloring, whether or not this table satisfies that all edges are not monochromatic, so that this mapping, such a mapping, can serve as a witness in this example. And the witness is polynomially long and can be verified in polynomial time. Can be verified in polynomial time because we only need to test all edges, whether they are non-monochromatic, and since they are at most polynomially, actually at most quadratically many edges, this can be done in polynomial time. And finally, checking that the binary length of that witness of that table is at most polynomial. And again, this can be seen because it requires a constant amount of memory, a constant number of bits, in order to encode this table in our setting as some kind of a combined natural number using the pairing function. So long story short, choose as X the entries in the table, the encoding of the graph, and choose as Y the encoding of this table that assigns to every vertex present its color, one of the 3 colors, and together this will form a witness which has at most polynomial length, and that can be verified in polynomial time. So far everything looks good, and in particular this class 3-colorable or 3-colorable thus belongs to this syntactic complexity class NP. And this immediately raises the question whether NP is optimal, whether this is the final answer. Remember our small hierarchy. Since the decision problem which has shown to belong to NP, then it must also belong to PSPACE, and it must also belong to exponential time, because generically, PSPACE includes all terminating decision problems in NP, which in turn includes all decision problems that can be solved in exponential time. But can it be done more efficiently, or are we overestimating the computational complexity of this problem? Is there maybe a more efficient algorithm that can get away without a witness, maybe an algorithm that decides whether a graph is three-colorable rather than just verifies it? And this turns out to be very delicate and famous open question in computational complexity theory. But before we will return to that later, let's consider some other graph problems and try to put them into this small complexity hierarchy. The first such graph problems that we consider is the Eulerian cycle problem. Eulerian cycle is a decision problem of some directed graph, and it's motivated and denoted and originated in the city of Königsberg, which Euler was interested in at that time. And Königsberg has like many cities of that time, has a river running through it, and there are bridges over this river, in this case 7 bridges. And the Eulerian cycle problem asks the following question: is it possible to traverse every single one of these bridges in polynomial time or not? And returning, is it possible to traverse all these bridges and returning to the starting point without crossing any bridge twice? Let me say it again in a different way. Is it possible to cross every single bridge precisely once and return to the starting point? And one way of approaching that problem is by turning it into a graph problem, namely turning the bridges into edges and turning the areas that are connected by such bridges into vertices, and ask whether it's possible to traverse this graph using, and here's the formalization. The Eulerian cycle problem is the set of all encodings of graphs that admit a Eulerian cycle in this sense. Encoding, now again referring to our standard way of encoding a graph without weight here, encoding a graph as a natural number. And also this problem can be seen to belong to the complexity class NP, because we can reformulate it equivalently into this syntactic form with the polynomial length and polynomial time decidable witness. And to see this, let's consider as witness such a Eulerian cycle, a sequence of edges traversed. How many edges are there in this sequence? Well, if the graph has m edges, then there are at most m edges in that sequence, and m, the number of edges, is always at most quadratic in the number n of vertices. So the number of edges is polynomial, and thus such a sequence of edges will have binary length encoding. Every edge will receive some integer, but the binary length of that integer will be at most logarithmic, and having polynomial quadratic number of edges, that means that such a witness will have at most polynomial length. And when given such a witness, is it not hard to verify that it is that the witness does constitute a Eulerian cycle, namely by simply verifying that it traverses every single edge exactly one. That's about the Eulerian cycle problem. And now we're moving on to a small, very related problem, small change, namely Hamilton cycle problem. The difference is that now the condition is that every vertex be traversed precisely once, whereas for Eulerian cycle, it's every edge that must be traversed exactly once. So the Hamilton cycle problem is also formalized similarly as a set of all codings of graphs that admit a Hamiltonian cycle. And it also equally easily can be brought into this syntactic form of the complexity class NP. Now we use as witness simply the Hamiltonian cycle, that is the sequence of vertices in the order in which they are visited. And similarly, it's easy to see that this sequence has a total length, which is polynomial in the number of vertices and thus in the binary coding length of the graph. And being a Hamiltonian cycle is also easily verified when giving such a sequence of vertices. Just make sure that every vertex of the graph occurs and is visited precisely once, so that also this decision problem belongs to this syntactic complexity class NP. But, and that's a subtle thing, this estimate, this classification of the two decision problems into our small complexity hierarchy, P, NP, polynomial space, exponential running time. This classification is not optimal because at least from one of the two problems can actually be decided rather than just verified in polynomial time. Namely, specifically, the Eulerian cycle problem can be decided in polynomial time. It's possible to decide in polynomial time with a graph admits a Eulerian cycle because of a combinatorial equivalent characterization of Eulerian cycle property. Namely, a graph admits a Eulerian cycle if and only if it is first connected. That's a necessary condition, right? If the graph is not connected, then it's impossible to traverse all edges, to even reach all edges, with the exception of the case where there's some isolated vertices. But this is not a serious exception, because we can easily pre-process the graph and throw away all isolated vertices, because they don't affect whether the graph has a Eulerian cycle or not. So let's just suppose the graph has no isolated vertices. Then being connected is a necessary condition. And another necessary condition is that every vertex has an even number of edges incident to it. Let me say that again. It's necessary for a graph to have a Eulerian cycle that every vertex has an even number of undirected edges incident to it. Why is that so? Because if the graph does admit the Eulerian cycle and the Eulerian cycle enters a vertex through some edge, then it must also leave the vertex again, right? Through a different edge. And maybe during the Eulerian cycle, that same vertex gets visited again, but if it does so, then it does through a different edge, because no edge can be visited twice, and also must leave again a second time, again through a different edge, because no edge must be visited twice. So that means where to every vertex, whenever in a Eulerian cycle a vertex gets visited, then it's also left. And if it's visited a certain number of times, then it's entered and left twice as often, and therefore an even number of times. So to summarize, we now have identified two simple necessary conditions for a graph to admit a Eulerian cycle. Namely, it must be connected after we've removed isolated verses, and it must have an even number of edges incident to each vertex. And now it's a combinatorial statement that these two conditions together are not just necessary, but also sufficient. I'm not going to prove that because that's a subject of combinatorics, but based on this fact that we use here without further reference, we have arrived at a combinatorial characterization of a graph having a Eulerian cycle, and a characterization which is algorithmically much easier to verify than the original definition, the naive approach of checking whether a graph has a Eulerian cycle. Namely, based on this mathematical insight, we cannot test a superficially entirely different property than Eulerian cycle. We test whether the graph is connected, which can easily be done using, for example, Dijkstra's method. And we test whether every vertex has an even number of edges incident to it, which again can be tested very easily by looking at the adjacency matrix representation encoding. And this algorithm thus runs in polynomial time, and by the combinatorial theorem, it is equivalent, and thus the algorithm also tests the original property of being Eulerian in polynomial time. So to summarize, based on this mathematical combinatorial insight, we can see that actually the Eulerian cycle problem is not just in NP, it is still is, and this is and remains true, but it's actually in P, in the smaller class, according to our hierarchy, as you remember. So that now we've improved the complexity classification, and we're stuck with the natural question: how about the Hamilton cycle problem? Can this classification to belong to NP, can this be improved as well? And the answer is, I don't know. Even worse, it's not just not just me who doesn't know, but nobody knows. And we'll understand later in the course of this chapter 4 why this is such a difficult question. And for those who are already familiar with it, because Hamilton cycle problem can be shown to be NP complete. So whether or not this can be solved in polynomial time is equivalent to the P versus NP millennium problem, and therefore not known. Okay, so to summarize today's lecture, we have talked about wild plus programs as a formalization of algorithms, and in particular of polynomial time algorithms. We've talked about polynomial space algorithms that use a polynomial amount of memory. We've recalled and established this small hierarchy, starting with polynomial time decidable problems, moving on to NP polynomial time verifiable problems defined syntactically, then polynomial space decidable problems, and finally exponential space decidable problem. We've established that each of these classes is contained in the next one, and we started classifying certain graph problems into these classes. We've shown that the three coloring problem of a graph encoded in the appropriate way belongs to this class NP. We've shown that the Eulerian cycle problem belongs to this class NP. We've shown that the Hamilton cycle problem belongs to this graph NP, but we have been able to improve the Eulerian cycle classification, not just in NP, but actually in P. And that raises a question whether also Hamilton cycle classification can be improved to belong to the class P, whether the three coloring problem can be improved to belong to the class P. And here are some more decision problems that we're going to look at in the next session. So here's Eulerian cycle versus Hamilton cycle problem. Next, we're going to look at edge cover versus vertex cover, which are two other decision problems. Edge cover problem can be informally described as the following question, as an optimization, namely as a minimization problem. Given a graph, find a smallest subset of edges such that any vertex is adjacent to at least one of the edges in the smaller subset. So the intuition, try to cover all vertices in the graph by as few of the edges that are already present in the graph, or put differently, try to throw away as many edges as possible in the graph to arrive and still be able to cover, not necessarily connected, but to cover all vertices with it as at least one endpoint of this small subset. And smallest subset here means it's a minimization and optimization problem, which is a function problem, not a decision problem. But here, remember, we only talk about decision problems. How can we turn that optimization, that function problem, where the output is a smallest subset, which is not even required to be unique, cannot be imposed to be unique. How can we turn that into a decision problem? And before we do that, consider here two examples that illustrate a graph which has different size edge covers. So the first graph here is this graph, and indicated in red is a edge cover. The three red edges cover all vertices. Every vertex is an endpoint to some of the three edges, right? And here you see another graph with also 6 vertices, same number of vertices here. But here it requires a larger edge cover. I mean, here 4 edges of the edges are required to cover all the vertices. Intuitively, we need each one of these edges in order to cover these 3 vertices. These will also cover this vertex. And we need an additional edge in order to cover these 2 vertices. So here, the smallest edge cover here is 4, and here smallest edge cover is 3. And as I said, this is optimization and a minimization problem, and we turn that into a decision problem in the following way by considering the following set as a decision problem: encoding of the set of vertices of the input graph, encoding of the set of edges, the light ones here, and an encoding of an integer k, where the question is, does there exist an edge cover of size at most k? So we turn this optimization problem, find the smallest edge cover, into a decision problem by adding a new input parameter k and asking whether there exists an edge cover of size at most k. And now it's a decision problem, right? And this is what you see formulated here. Some subtle point I'd like to emphasize. Here we are not asking whether there exists an edge cover of size at most k, but one of size exactly k. But this is a no loss of generality, because we can always throw in some dummy edges, provided that the original graph has at least k edges. Otherwise, the whole problem is trivial anyway, because we can easily check whether the graph has, original graph has k edges or not. So long story short, also this problem belongs to the class NP. It's already formulated in this way, where here F, the subset of edges, that's our witness, right? Our witness, it has polynomial length, 1 bit for each edge in the original graph, indicating whether this edge belongs to the edge cover or not, and verifying whether a given set of edges is an edge cover or not. That's easy. Just to make sure every edge given belongs to the original graph, and make sure that every vertex is endpoint of one of the edges in this set, so that this indeed belongs to NP. And the other variant of the problem that we consider is the vertex cover problem, which is kind of dual, if you like. Here we want to cover the edges with vertices, whereas originally we wanted to cover the vertices with edges. The vertex cover problem dually asks whether there exists a subset of the vertices of size at most k, such that every edge has at least one endpoint in this small subset of the vertices. And this is also easily seen to belong to NP. It's also already formulated in this syntactic form. Again, raising the question whether this classification in NP is optimal or not. And it turns out that the first one is not optimal. There's a polynomial time algorithm for the edge cover problem, namely greedily calculate a maximum matching and then greedily extend that to maximum edging. That is a polynomial time algorithm, but our time is up. I'm going to recall and resume here the next time. Thank you very much for your attention, and see you on Thursday.